So there's no question.
The distance between 2 points?
Yeah, we'll do that after.
Okay. First of all, how would I graph that line right there? Where would I start?
3.
If I tell you the standard format of a linear equation is that, what is B?
B is the y-intercept.
Okay. I've written this in the standard format. So let's start at the y-intercept.
So it's 4.
That point has to be on our line. And you can tell because when x is 0, y is 4. Well, when you have a point that's on the y-intercept, x is 0 always. If I have a point on the x-intercept, y is 0. So that fact is pretty useful, that y-intercepts are where x is 0, x-intercepts are where y is 0. And now what do I do? Once I got the y-intercept. What's that?
That's the slope.
That's the next most important thing.
The 3/1.
Okay, so how do I draw my next point on this line?
You could go down 3 into the left 1.
Okay.
Which would be...
And just connect 2 points, and any 2 points makes a straight line.
Right.
So it's relatively easy when it's in slope-intercept format, and that's what that's called, is slope-intercept, because we have the slope and we have the intercept. Okay. What else did you say besides graphing? You said it and I forgot.
So let's take those 2 points, the same 2 points.
Distance between 2 points.
Right.
Okay. First of all, I'm going to just make up 2 points. Okay. Now I'm going to graph them. I don't have to graph them exactly. I just got to be approximate. So the distance between those 2 lines is the distance formula. What is the distance formula equal to?
x1 minus x2.
Okay, it starts out with square root. And then
Square root.
x1 minus x sub 2 squared plus y1 minus y sub 2 squared. Now, let me help you memorize this. That's a mouthful to memorize. Okay, a lot of people have trouble memorizing that whole thing. But notice that the distance is always the hypotenuse of the triangle that you would create.
Right.
Okay. And
So
by the Pythagorean theorem, you know if that's C, A, and B, that C squared equals A squared plus B squared.
Right, so it's a play on the Pythagorean theorem.
It's exactly the Pythagorean theorem. Only instead of A, notice what A is. A is the difference in the y coordinates.
Right.
B is the difference in the x coordinates. So this is B, that is A.
And it doesn't matter which x you put first, right?
No, it really doesn't. And the reason is that if you happen to switch these up,
It's the same.
well, once it's squared, it's the same. In other words, 2 minus a minus 4 is 6, squared is 36. Minus 4 minus 2 is minus 6, squared is still 36. So the order you do it doesn't matter. Unlike slope, if you're figuring up slope, you need to make sure you do it the same order in the numerator as you do the denominator.
So no matter what, it's going to be positive for both.
Correct. So let's plug in. But just remember that this distance formula has to look exactly like what the hypotenuse. In other words, when you solve for the hypotenuse of a triangle, of a right triangle, it's always the square root of something. Always starts square root of. So what are my two things that I'm going to square and add together inside?
-4 minus 2.
Okay, what's that number?
That number is -6 squared,
Okay.
which is 36, plus just 5 minus 3, which is 2.
So the distance is the square root of 40. Simplify that.
Square root of 40. Is that a number I should know? Should I have in my head?
You definitely need to be able to simplify radicals. That I'm pretty sure of. Let's talk about doing that.
You mean square both sides?
No? Square root of 40. This is based on the principle that the square root of a times b is the square root of a times the square root of b. Okay? So think of 40 as being the product of two numbers. Well, how about square root of 4 times square root of 10? The reason I broke it up into 4 and 10 is because 4 is a perfect square number. In other words, I can now take square root of 4 and that's 2. And that's the way you would always call square root of 40. You would never give this as an answer because it's not simplified. And simplification means pulling out a whole number if you can. Okay? Now, notice that 40 is also 5 times 8, but that doesn't do very much good because it's hard to pull a whole number out of that. Neither one of those is perfect squares. Okay? How about this?
That's 5 and 2.
But that's not simplified. In other words, that's actually more complicated. So you don't simplify square root of 10 unless you can pull a whole number out of it. That's the rule.
Unless you're trying to get it at square root of 5 or square root of 2 for some reason.
What's that?
Unless you need a square root of 5 or square root of 2 for some reason.
Well, I'm talking about just simplifying final answers. Okay? In other words, this is always the answer you would give, not ever this.
Okay.
Okay? You only simplify it if you can pull out a whole number. What is this?
You got
Think of factors of 32.
8 and 4.
Okay?
Which is 2 times square root of 8.
That works, except now square root of 8 is not simplified.
So you can separate that again.
Go ahead.
2 and 4. So then you have 4 square root of 2.
Correct. Now, notice that had you noticed that 16 is a divisor of 32, we could have done it all in one step by breaking it up into 16 times 2. And then immediately you get to that step. So it's not a requirement to factor it where you have the largest perfect square possible, but it does save time. But even if you don't, you can always whittle it down. So the numbers that are really important when you're simplifying radicals are these numbers here. the perfect square number. In other words, if I said the square root of 128, what's that going to be?
2 and 64.
So 8 root 2. Same thing with division. Well, not really the same thing, but same starting principle. If I have the square root of a over b, that's the same as the square root of a divided by the square root of b. So if I said, what's the square root of 25/9? Well, who knows what the square root of 25/9 is, but if we look at it like this, it's real easy. What is it?
It's 5 over 3.
Correct. And that's how you would do it, is break it up into that, like that, and then you have two perfect squares. Okay. Let's talk about graphing on the XY coordinate plane. You have an equation that has a slope of 2, and this point is on the line. It's a linear equation. What is that equation? This is something I know you absolutely have to know how to do.
Y equals 8x plus 3?
No? You can use the slope-intercept form to solve it, but here's the way you have to do it. We know it's y equal mx plus b, and we know what m is. M is 2. Okay? So I know that much of the equation.
Right.
How do I figure out b? I also know this point is on the equation. And what that means is that I can substitute 4 for x and 3 for y. No matter what the equation is, I know that when x is 4, y is going to be 3.
Well, then you could just substitute it.
That's what you want to do. So you got 3 equals 2 times 4 plus b. Now b equals minus 5, and now we know our entire equation. Y equals 2x minus 5. So when you have slope and one point, you can always figure out the equation doing this technique. There's other techniques that are actually a little more direct, but it involves the other format of a line, which is slope, point slope. Let me just tell you point slope and see if you've had it. The point slope format is the following. Y minus y1 equals the slope times x minus x1. Now it's called, have you had point slope?
I don't know. It looks like it.
You probably have. It's called point slope for a reason. We have a slope and we have a point. Okay, well, I can fill in directly. Y minus y sub 1 is 3 equals the slope, and x minus 4, and there's our answer in one step. I didn't have to go through this process of solving for b. And this is a perfectly fine answer. Notice that it gives you the same as this up here. They're both the same equation of the line. It's just this is written in point slope format. This is written in slope-intercept format. So if they don't specify, either answer is correct. If they say, give me the answer in slope-intercept format, then you want it like this. If they say, give it to me in point-slope format, you want it like this. Now, in case you forget what point-slope format looks like, notice that if I divide both sides by x minus x sub 1, I get slope equals rise over run.
Okay.
Okay. I'm sure you've had to deal with graphing a lot more equations than just linear ones.
Yeah. I don't know. I don't remember having to graph quadratics. That's a parabola, right?
Uh-huh. In other words, I'm sure you did, but
In algebra 2, I think I did.
there's the basic formula for the equation of a parabola, and goes through 0, 0. And if it's a negative sign, it's going to point down. If it's a positive sign in front of the x squared term, it points up. And it covers all kinds of type parabolas. In other words, my parabola might look like this. Okay, well, that's still going to be a parabola. It's just not going to have its origin it's not going to have its vertex at the origin.
It's going to be 2 up and 1 to the left.
Now let's see, this factors into x minus 1 times x minus 1. So I can tell that when x is 1, y is 0. So it has to look like this. And not that it's always that easy to graph a parabola, it isn't. This one I made up such that it was 2 factors that were the same. But let's say I had that, 7 and 10. Well, now this doesn't factor. It factors into x minus 2 and x minus 5. And now what that tells me is I have x-intercepts at plus 2 and plus 5. Well, what kind of parabola could be that? Something like this. Okay.
With 2 circles.
Well, this is in x-intercept format, where you have 2 linear factors. Hold on a second. Let me get my dog out of here. Hi. Hi. Come here. Hi. Come here. It's thundering out. She barks whenever it thunders. Now, let's, there's basically 10 basic equations that you want to know what the graph looks like. There's linear, there's quadratic, there's cubic, that's y equal x cubed. There's the square root function, looks like that. In other words, that would be y equals square root of x. What's that?
That's an exponential function, isn't it?
No, it looks a little bit like an exponential function, but it's the square root function. Here's what an exponential function looks like. If I say y equal 2 to the x power, in other words, an exponential function is when your variable is in the exponent. It's not an algebraic equation anymore. That's what an exponential function looks like. And the inverse of an exponential function is a log function. And what a log function looks like is more similar to the square root function. the log function looks like this. But quite different, the log function can have negative y's. The square root function cannot. In other words, the square root function, both x has to be positive and y always has to be positive. Whereas the log function, this is negative whenever x is between 0 and 1, and it's positive whenever x is greater than 1. And x can never be 0 and x can never be negative when you have the logarithmic function. What are some other very important functions that you would know? The hyperbolic function. That's y equal 1 over x. And this is actually a conic section, but the very first time you get exposed to this is this simple basic parent function y equal 1 over x. That is a hyperbola. Only instead of a hyperbola where the things look like that or like this, they're diagonal to one another in its simplest form. I don't know if this is what you want to review or not. I'm just kind of shooting in the dark here, Max.
Yeah. I want to touch on inequalities.
Okay, good. Let's talk about some inequalities and absolute values.
Yeah.
Let's take this. How would I solve that?
You would solve it mostly as a regular algebraic equation.
Okay, what's the next line?
Minus 2x minus 2x is greater than 2.
And the next line. Or what's the next thing you're going to do?
You're going to divide by a negative and flip the sign.
Okay, so our final answer is what?
X is less than negative 1.
Okay. So you know how to solve your basic inequality. Let's make sure you know absolute value. If I have an absolute value that's an equation, how do I solve that? Well, first of all, let me make one that's possible. Okay. Since the absolute value of a number can never be negative 10. But there's a specific way to go about solving these. And what they are is you take whatever's inside the absolute value. In other words, the first step is just to rewrite it without the absolute value sign. And then there's an or. And the or part is the same, whatever's inside the absolute value, but now it's equal to minus 10. And now solve each of these equations. Well, x equals 7 or x equals minus 13. And if you plug in 7, you'll notice that it's a true statement. And if you plug in minus 13, it's a true statement.
Okay.
Okay? So the process when you have absolute value equations is always going to produce 2, at least, equations that you have to then solve.
What if on the right side of the original equation it's like x plus 2? I mean, okay, x plus 2x.
X plus 2, we'll just do that. Okay? Well, now what I can say is that x plus 3 equals x plus 2. That's always the first start. or x plus 3 equals the negative of x plus 2, like that.
So negative x and negative 2.
Correct. But notice this one doesn't have a solution. If I cross out the x's, which I certainly could do, I now have one number equals a different number. So that doesn't have a solution. Does the right side? Maybe. We got x plus 3 equals negative x minus 2. You can bring the x over, so now I have 2x equals negative 5. Yes, that one does have a solution. So this would be the only solution to this problem. You can never have a solution that ends up with one number equaling another number. That means there's no solution to that part of it. Now, let's deal with the hardest part, and that's absolute values with inequalities. Something like that. Well, you do very similar thing as you would solve an absolute value with an equation. Is you're going to say x plus 3 is greater than 10. In other words, always this left side is exactly how you've written it without the absolute value sign.
Okay. Or
never change what's in the middle. Always leave that the same. But now the right side of it, you have to do two things. You have to not only make it a minus 10, but you have to change the direction of the inequality.
Because you're like dividing by negative 1 almost?
I don't even know what the explanation for it is. It's just the way you solve these. Notice what happens. I get x is greater than 7 or x is less than minus 13. And you can see that both of those are solutions. Put in 8 for x. Well, absolute value of 11 is greater than the absolute value of 10. Put in minus 15 for x. Well, the absolute value of minus 12 is greater than 10. So when you're solving a combination of absolute value and an inequality, always use this method. And always write your two equations side by side like I do here.
And you graph this on a number line, right?
Well, yep. You do graph it on a number line, and this is what the graph would, here's what the graph would look like for this particular line. Yeah.
It would be an open circle on 7 and all the way right. And then an open circle on negative 13 and all the way left.
Correct. And that would be the graph of that. And if you had to put it in interval notation, are you familiar with interval notation?
Yes, it would be 7 comma infinity.
Negative, always start with negative infinity if it's in the field, and it is. So negative infinity to minus 13 with a parentheses in combination with what?
In combination with 7 comma infinity.
And parentheses always go next to infinities.
Right.
Okay. If I change this to greater than or equal to 10, so that this is my solution now just makes these closed dots instead of open ones. And it makes these brackets instead of parentheses.
Right.
Okay. Now, if you have something with an absolute value in it that's not isolated, like this, well, your first step is to always to get that isolated. Once you get it isolated, apply the two rules. In other words, break it into the two equations that I just was describing how to do. But you can't do anything unless you get it isolated. It's a little like square roots. if I give you this, how do you solve that?
Square both sides.
Okay, what's the next line?
X plus 5 equals 10.
So x, excuse me,
No.
you got to square
X
both
plus
sides.
100. Yeah.
X plus 5 equals 100, which means x equals 95. And sure enough, 95 plus 5 is 100, square root of 100 is 10. But if they had other stuff on this problem, like minus x equals 10, well, now you got to move the x over there before you can square both sides. Okay, now I can square both sides, right?
Right.
Well, when I square both sides, I get this on the left, but over here I get x squared plus 20x plus 100. So now I have a quadratic that I'm dealing with. Okay, well, how do I solve a quadratic? I get everything on one side, 0 on the other. So I'm going to move everything to the right, leaving 0 on the left.
So x squared plus 19x plus 95.
Yeah, and that's probably not factored easily, so I would apply the quadratic formula to it. You know the quadratic formula?
B plus or minus.
It's actually minus b plus
Minus b plus or minus the square root of a. I don't know.
I can't imagine that you wouldn't have to know that by heart, but maybe not. I don't know. It's something you want to memorize if you don't know it well. Part of an easy way to memorizing it is to notice that the first half of it, minus b over 2a, that's how you find the vertex of a quadratic.
Okay.
So if you remember that the x-coordinate of the vertex of a quadratic is this, it helps with memorizing the quadratic formula, and vice versa. In other words, if you forget what the vertex of a quadratic is, say I wanted to know where the vertex of that quadratic we got was, well, the x-coordinate is going to be minus 19 over 2. That's the x-coordinate of it, minus b over 2a. That only gives you the x-coordinate. In order to get the y-coordinate, you would have to plug this in for x to solve for y. Okay, here, let me look at my book here. That stuff that we've been covering is in my chapter 1 of
Yeah, my chapter 1 too.
Pre-Calc. Chapter 2 is polynomials, powers, and rational functions, imaginary numbers. Are imaginary numbers going to be on your test?
No.
Okay.
My chapter 2 is functions and graphs matching equations to graphs.
Okay, and transformations maybe?
Possibly, but I don't know that term.
Well, usually when they want you to match a function to a graph, it's something like negative e to the x. Okay? I'll give you 2 graphs over here. There's one. And there's the other. Which one is that? Y,
one to the
y
right.
equal negative e to the x is which graph?
The one to the right.
Yeah, because what this negative sign means is it's a reflection of the parent graph over the x-axis.
Right.
So that's all I did, was reflect it over the x-axis to get the one on the right. But what if I told you that e to the minus x? Well, that's a reflection over the y-axis. So it would look like that.
Okay.
Now, there are 6 total types of transformations. You can have reflections over either axis. You can have a vertical shift or a vertical stretch, or you can have a horizontal shift or a horizontal stretch. So in other words, if I gave you something that had been shifted, and this is what they always want you to do, is they want you to tell them, how has this been shifted?
Shifted one to the left.
No. This is the horizontal shift, the part that's inside the original function.
Oh. So it shifted one up.
One up, that's a vertical shift. And this 2 is a stretch factor. Okay? So
yeah.
If I were to plot each of these, well, first of all, the parent function is y equal x squared, just the parabola. So the first thing I'm going to do is shift it 3, and it's actually to the right, because the standard is x minus h. So if h is a positive 3, which it is here, it's a shift to the right by 3 units. So the first shift would be to there, and then the shift up by 1 would be to there, and then the vertical stretch by a factor of 2 would be making it skinnier, going in the same vertex, but it would be skinnier instead of flat or fatter.
Okay.
Well, given a bunch of functions that have been transformed, in other words, they've either been reflected or shifted or stretched, figuring out what has been done to it and which function it matches. In other words, they may give you 6 equations, kind of like that, and 6 graphs, and say which equation goes with which graph. And it's not that easy to work backwards. I have a pretty good way of describing it to you, but it's fairly complicated, and it would probably take the rest of our time to go through each of the 6 transformations. And how you know, when you look at this, what you, here, let me call this f of x. Let me just tell you basically. Well, what this is 2 times f of x. It's actually 2 times f of x minus 3 plus 1. That's what it is. And what you need to know is that anything inside the parentheses is a horizontal shift or stretch. Anything outside the parentheses is a vertical. That's going to be a vertical stretch, that's going to be a vertical shift, that's going to be a horizontal shift. If I wanted a horizontal stretch, I'd put a number in front of the x. So I put a 4 right there inside the parentheses, and now I have a horizontal compression also. So it all comes down to how the function looks under f of x notation.
If there was a negative on the first part, like before the parentheses, if it was like a -2, that is fatter than the regular equation, right?
Well, what you're talking about is that.
Right.
That is a reflection over x. If it's this, that is a reflection over y.
Wait, no, if it was like f of x equals -2 of the quantity x plus 3, that -2 makes the graph fatter, right?
Well, let's square it, because a straight line isn't going to get fatter or skinnier. So what we had there was linear. But if it's this, then it makes it skinnier. But the fact is what this is negative f of x plus 3. If my original function was g of x equals x squared. In other words, there's your parent function for a quadratic. And now they give you this function, and they want to know, well, what happened to the parabola? Well, I have to know to be able to write it like that, to figure it out. In other words, I always want to write it how I would write it under f of x notation.
Right.
And it's not so important. The perfect function to use is this one. G of x is equal to e to the x. Okay? And the reason is all 6 transformations result in a different looking curve. The first 2, well, that's this. That's a reflection over the x-axis. The second one looks like this. That's this. A reflection over the y-axis. In other words, if they give you this, you've got to be able to talk about it in terms of f of x or g of x in order to know what's being done to it.
Okay.
Let me keep
But
going.
then how would you make...
That's the 2 reflections. If I want a vertical expansion, then I'm going to do this. And that might look like this. That 3 is a vertical stretch factor. If I want a horizontal compression or expansion, it would write like that, and that would be this. So if I see e to the 2x, I know that 2 is a horizontal compression factor. It takes my e to the x curve, which looks like this, and makes it compress it. So it's like that.
Okay. And I guess if it was a fraction, then it would make it fatter.
Yes, very good. If this is a fraction, it makes it fatter. Now notice this operates in exactly the opposite way that this does. If this number is greater than 1, it makes it skinnier. If it's between 0 and 1, it makes it fatter. Well, this number, if it's greater than 1, makes it skinnier. If it's between 0 and 1, it makes it fatter. So they have the opposite effect, basically, at least in terms of words. If you're talking about something being stretched or compressed. There's actually, this is called a stretch or shrink factor. Stretch if it's greater than 1, shrink if it's between 0 and 1. This is called a stretch or shrink factor. Shrink if it's greater than 1, stretch if it's between 0 and 1.
Okay.
Okay? That's 4 things. That's 1, 2 reflections, 2 vertical actions, and finally there's 2 more, and that's the horizontal effects. Hold on a second here. In other words, there's 6 total transformations. Well, the 2 more are going to look like this. If I have, no, excuse me, hold on, I screwed up here. This is a vertical stretch. This is a horizontal compression. Well, there's a vertical shift, which is the easy one. That's g of x plus some number. For example, e to the x plus 1. That's the e to the x curve shifted up 1 unit. And if I saw this, I would have to know that I was looking at g of x plus some constant. And finally, there's only one other thing you can do, and that's a horizontal shift, and that would be this. In other words, if I had e to the x minus 1. Notice how each e function looks different. All 6, and you got to go, in other words, you almost have to look at the e to the x function to see all 6 of these changes. But the trick in all of them is being able to take your transformed function and figure out how it was transformed. So if I give you something that's this, that has everything you can possibly do to that function. This is what?
That's a shrink.
It's a stretch because it's this case right here. The 3 is in front of the function. It's not part of it. I'm not taking 3x. I'm not taking 3 times e to the x or e to the 3x. In other words, if the number is in front of the function, it's a vertical stretch or shrink factor. Also, always do your reflections first. We got 2 reflections here. Very first thing I'm going to do is take my e to the x function and flip it over the x-axis because of this negative sign. The very second thing I'm going to do is take this negative sign and flip it over the y-axis. If you do not do your reflections first, you will end up with occasionally the wrong graph. So the only thing, and it doesn't matter which reflection you do first, if there are reflections to be done, do them first.
Okay.
Okay? And then after that, well, that's a multiplier inside. In other words, that looks like that, right? And it's like we already did the reflection, but the multiplier is inside, so that is a compression factor by a factor of 4. This is a stretch, that's a compression. And then we have the x minus 1, that's a horizontal shift to the right 1 unit because it looks like this. It looks like that one on the very bottom. It's g of x minus or plus some constant. And finally, the plus 2 looks like this. It's just the function with a vertical shift.
Okay.
So, if you wanted to memorize anything, what you want to memorize is these 6 alterations and know what each of them does. There's 2 reflections, 2 vertical alterations, and 2 horizontal. So if you kind of think of it like that, it makes it easier to remember that there are 6 and how to break them up. And some of them can get really quite difficult when you start dealing with difficult functions like greatest integer functions. In other words, I'm not going to get into this because I doubt that you'll have this, but what's the effect of the 2?
That's vertical.
Horizontal. It's inside the function. Anything inside the function is going to be horizontally affected. The 3 is outside the function. In other words, if I had to write this in f of x notation, if g of x was equal to the greatest integer function, like that, and I had to write this as some f of x, it would be f of 2x, that's what goes inside, minus 3. That's what this function is. And that's what you have to be able to do. So you have to be able to take a function and figure out how it would be written in f of x notation, and then interpret this. That's a horizontal compression by a factor of 2, and that's a vertical shift down by a factor of 3. In other words, once you get the function expressed in function notation, then it's all you have to do is know those 6 things, how to, what each one means. All right, is there anything else? Domain and range. Surely you're going to have to talk about that or know that. Yes? No?
Yes. Domain is x-axis. And
I'm just going to give you some functions and you tell me the domain.
Okay.
It's the domain.
Everything greater than 0. No. Everything greater than -3.
Correct. In other words, what you want to do whenever you see something like this is take whatever's inside the radical and force it to be greater than or equal to 0, and then solve it. Well, what does that mean? That means x is greater than or equal to -3, and that is your domain.
Except -3, can you take the square root of 0?
Yes, you can.
Okay.
Okay. There is a function that's more restrictive than the square root function, and that's the log function. You cannot, if I give you this function,
Has to be greater than 0.
it has to be greater than 0. It can't even be equal to 0. So the log function is more restrictive than the square root function is. But make that really complicated, like x plus 1 over x squared minus 6 plus 10. Well, now how would you solve it? You would take that entire thing, force it to be greater than or equal to 0, and then solve it. And that would be how you would get your domain. So you just take whatever's inside the radical sign. Okay. Now, how about this? Oh, let's back up 1 minute. What's the range on that?
The
range is what y can be.
All real numbers.
Y can't be negative.
Oh, because it's a square root, right.
Right. In other words, that's why when I graphed it, I started at 0, 0. Because x can never be, and this is y equal square root of x. But x can never be negative and y can never be negative. Well, y can never be negative even if the inside is not x, even if it's x plus 3. That can only be positive. So if I gave you this function, express this. In other words, if I told you g of x was the square root of x, then how would this be written in f of x notation?
In f of x notation?
Uh-huh.
G of x plus 3?
No, it would be f of x plus 3.
Oh.
In other words, this would represent that, which is, it's the square root function horizontally shifted 3 units to the left. So if I wanted to graph that, or if I wanted to identify a graph, I know it's my square root function shifted 3 units to the left. Nothing else is happening to it. It looks exactly as it did. only it's shifted 3 units to the left. And notice this graph, x has to be greater than or equal to -3, and y has to be greater than or equal to 0. But
Okay.
this is what I'm saying is that if they give you that function, you have to know that this is how you would write it with f of x notation. Actually, if f of x was that, excuse me.
Okay, that's what was confusing.
Yeah, I'm sorry.
It's okay.
If f of x was this, then this would be written f of x plus 3.
Right.
All right.
All right.
Well, if you don't get an A, it won't be for lack of trying. I'll give you that, Max. You do know how to put in the effort. So good luck on your final. And maybe I'll talk. What are you taking next year? Are you going to take calc?
Yeah, I'm taking calc.
Good. Well, I'd love to work with you next semester.
Yeah, I might even be taking it online, so I'm not sure. You might be getting a lot more sessions from me.
Okay. Well, I'm going to have a reduction in price for the 3 summer months, June, July, and August.
Okay.
It's only going to be $20 per hour instead of 32. I don't get I don't get a lot of work in the summer, so anything I can do to promote it, and that's what I'm doing to promote it. And you'll get an email on that by probably tomorrow. I'm going to send out the emails. But for June, July, and August, it's $20 per hour.
Okay.
For online. And if you want to spend some time this summer preparing for calculus, I would actually really advise that. Getting a head start on calculus is huge. Most people have to take calculus twice to even get a grasp of understanding it. So if you can get a little head start on it, you'll be miles ahead, let me tell you.
All right.
All right, Matt.
All right, well, thank you.
You're welcome. Have a good summer.
You too.